Greetings everyone and welcome back to our video series about Qt containers in Qt 5 and Qt 6. I am Giuseppe D'Angelo and in today's video we're going to discuss implicit sharing in detail. So what is implicit sharing? If you open the documentation of many classes in Qt, you may find a note somewhere that says this class is implicitly shared. And you may be left wondering, okay, so what is that all about? It's fairly simple, actually. Implicit sharing is nothing but a very fancy name for something that we all know, which is reference counting. Okay, instances of implicitly shared, I will never be able to say it correctly. Instances of implicitly shared classes simply keep a counter inside of them, and this counter counts how many references are alive at that moment, pointing to that particular instance. So that's what reference counting is in a nutshell. Implicit sharing is that combined with copy on write, meaning that when you try to write into an implicit shared object, if that object is actually shared, then you're going to copy it, or to say deep copy it, and do your modifications. This particular feature, implicit sharing, is found in pretty much all of the containers, but also very at large in Qt. Most Qt value classes actually feature this implicit sharing mechanism. How is this implemented? It's implemented in a very simple way. If you take any Qt value class that you like, so QVector, QList, but also QString or QImage and such, these classes are nothing but a small pointer to a private part called a private implementation part or pimple. And this part is heap allocated and contains at least two different things. It contains the reference counter for the reference counting mechanism for implicit sharing, plus, of course, the class-specific data. So if it's a vector, the list of elements, the size, the capacity, stuff like that. If it's an image, the image data, the format, the width, the height, and stuff like that. Okay, so it's pretty straightforward stuff. Now, the interesting thing about implicit sharing is how it actually behaves at runtime. That is, how is this reference counter found in all the objects of implicitly shared classes manipulated throughout your application lifetime? There is a little set of rules, which I'm going to explain to you, but hopefully they just make sense, because this is, again, reference counting and copy on write. So the way this works is like this. When you create an instance of an implicitly shared class, that instance starts its lifetime with the reference counter set to 1. And that's because there is only one instance referring to that particular payload, and so the reference counter is indeed 1. Now, when you take a copy of a class, so you have a vector and you take a copy of it, you don't do any deep copies. All you're going to do is simply take that reference counter and increment it by 1. So if it was 25 before, now it becomes 26. That's all doing a copy entails. It's super cheap if you think about it. There are no memory allocations, there are no deep copy of the data. All that Qt does is follow the pointer, follow the pimple, and increment the reference counter. Pretty straightforward. When you destroy an object, what happens? Well, destruction means, again, follow this pointer, go to the reference counter, and decrement the counter by 1. So destruction is also pretty cheap. However, if that reference counter reaches 0, then you should know that there are no other references alive pointing to that particular payload, and so that's the moment when you actually should deallocate the payload. And by you, of course, I mean Qt. Qt will deallocate a value class payload when the reference counter drops to 0, because that means that the user has destroyed all the implicitly shared references to that particular payload. So far, so good. So far, everything is simple. Now comes the twist, or the tricky part. What happens when you actually use this object? So when you have an object and you call some functions on it, this is where the behavior changes, depending on whether you call a const function, so a const method, or a non-const method. If you call a const method, everything's fine and everything's simple because you do nothing. You just access the pinball and read the data that you need to read. Const functions are not supposed to mutate the object, right? That's why they're called const. And so you can always go there and read the data that you need to read without worrying about whether that particular instance is shared amongst other instances or not. Super cheap. But if you want to modify your value, your container, your string, your image, that's when things become slightly more complex. Because when you want to modify something, that means you're going to call a non-const method on your instance. Then there is a little check that you must do. That is, you must check whether your particular data is being shared between other variables or not. If that particular data is being shared, that is, if the reference counter is strictly greater than 1, then you must deep copy the data. That's when the copy on write mechanism happens. That's when the deep copy actually happens. It happens when you have a non-const access and the reference counter is greater than 1. Okay, so you're going to detach from the shared pinball, and the detach means allocate a new pinball, deep copy the payload, the new reference counter is set to 1, the old reference counter is decremented by 1, and if it reaches 0, then you're going to destroy it. And then everything you need to do, so your non-const mutation, whatever it is going to happen on the brand new copy, the copy you just did. All right, so that's a lot of things, but hopefully should explain what implicit sharing is and how it works. And actually, I'm going to repeat all of this by using a little diagram to explain myself much better. So let me visualize by using a little image here what I mean by manipulating a reference counter. Here, what I got is a Q vector of integers. I built it, and it contains the integers 10, 20, 30. Now, this particular vector, when you look at it in memory, looks like something like this. The V object, the vector itself, is very small. It's just a pointer, okay? And the actual data, it's heap allocated in this data structure, which is actually the guts of a Q vector. So what does a Q vector contain? Well, it contains things like bookkeeping, size, capacity, various other stuff. It contains your data, the actual 10, 20, 30 integers, the actual payload. But it also contains somewhere this reference counter. And since this V vector has just been created, we know that its reference counter is 1. So now what I'm going to do is to manipulate this vector a little bit. So the first thing I'm going to do is to take a copy of that vector. I'm creating a vector called v2, and I'm assigning it, well, I'm building it, that's not assignment, that's construction from v. So copying v into v2 is an extremely cheap operation, unlike standard vector. Q vector, all it does is it follows the pointer pointed to v, it sets the same pointer into v2, and it increments the reference counter by 1. So it was 1 before, and now it's 2. That's all a copy entails. As you can see, it's very, very cheap. It's surely cheaper than allocating memory and doing a deep copy. And so that's pretty much why we do it all over the place in Qt, because it's very cheap to do. And now let me try mutate v2 somehow. So let me try applying a non-const function to this to show the detaching in action. So what I want to do here is to assign a new value at position 1, so the second position, into v2. Okay, in order to do that, I'm just using the subscript operator, the square bracket operator. Now, the square bracket operator, it's a function of QVector, and that function, in this particular instance, is a non-const function. So the first thing that happens is that Qt will check the reference counter value. If that reference counter is bigger than 1, it means that v2 is currently being shared with somebody else, which indeed it is in this case, it's shared with v. And this means you cannot do the modification right away. You need to do a deep copy. You need to detach v2 from the shared data. So you do the detach, okay? You create a new, you allocate a new block of memory. You deep copy all the data inside v2. The new reference counter is set to 1. The old one is decremented by 1 because it has lost an owner from a certain point of view. And now that you have your own private detached copy, that's when you can actually do the modification. And so that's when you can go in the second position and modify the 20 and make it 99. You may be left wondering at this point, why doing all of this? Isn't this a massive headache in terms of implementation, complexity, and whatnot? Maybe yes, but that's not something that should concern you because this is done internally in Qt for you, so that you don't see this complexity or the complexity of the code implementing implicit sharing. What you do see are just, if you want, the benefits, the pros, and also sometimes the cons. The pros of implicit sharing is that it makes writing code a lot simpler, especially code which is under very strict API and ABI guarantees. For instance, have you ever noticed that Qt classes, Qt functions happily return containers, strings, images by value? And they do that way before C++11 was a thing, even before move semantics were a thing. That's only possible because indeed returning by value, even if these are big objects, is cheap. Even if it does entail a copy, that copy is cheap to do. And if it does not entail a copy, if it's a move, then it's even cheaper. But the kick here is that Qt is also under this very strict ABI guarantee, meaning that it cannot just change return types of functions from values to references or stuff like that. That is completely not allowed within Qt. And so, well, this solves a very practical problem for Qt development. For you, well, you can use this, you can exploit this, because as I mentioned, the widest majority of Qt container classes and Qt value classes are indeed implicitly shared. So all the containers that we've seen in the previous video, pretty much all of them, except for that one qvar length array, but qvector, qlist, qmap, qhash, qset, all of them are implicitly shared. And also, as I said, the value classes, qstring, qpen, qbrush, qimage, they all feature this mechanism. So it's a common trait pretty much amongst all Qt classes, Qt value classes that is. And you can pretty much rely on this fact. Taking copies of Qt objects is very, very cheap to do. So is everything just that great and we should just be using this all over the place? Well, everything is great, but implicit sharing also comes with its fair share of downsides. Now, before I go into this, let me just put a huge warning sign over here, which is, please don't fall victim of the but sometimes syndrome. If you want to know what I'm talking about, I'm going to leave a link down in the video description. That is, I'm going to point out a few specific and peculiar downsides of implicit sharing, which may affect you or may not affect you. Still, implicit sharing may be a good trade-off for you. So don't be scared by the fact that, as all the trade-offs in this world, there are good sides and there are downsides. Okay, you should weight them appropriately and not just be scared by the following list of possible bad things that may happen. So the first thing is that you may have noticed when you try to use a Qt container inside a C++ range-based for loop, sometimes Qt Creator will spit out a warning telling you, hey, you should be using something else here because this for loop may detach your container. So what is that about? That's actually a bit tricky to explain, so I'm going to dedicate an entire video to that specific issue. But yes, it's kind of annoying that sometimes you have to deploy a little workaround when you want to just iterate over a Qt container. Another couple of more interesting aspects of this is that this detaching mechanism may have side effects that you don't intend to happen. In some cases, these may be just a performance hit, so something that you should be aware of that may cause an unexpected memory allocation. But in some very corner cases, these may actually introduce bugs inside your program. Don't be too scared. We have, again, workarounds for all of this. We have good practices to mitigate all these risks. And I'm going to also, of course, to discuss what these mitigation strategies are. But then, in a nutshell, if you try to hand out references to data inside a container, that reference may have side effects that you don't expect. As I said, it's easy to accidentally detach a container, so to cause a memory allocation that you didn't plan. and this accidental detaching may actually hide some bugs. So let's discuss these points in much more detail. The first point is about returning references to data inside a container. So if I have a container and I hand out a reference inside this container, Qt does not mark that container as not shareable. As an example of such a reference, for instance, an iterator pointing alive somewhere inside a container. Why should Qt need to mark the container as not shareable? We're going to see exactly what is why, but why is this happening? It's a correctness speed trade-off. Doing this would be extremely expensive for the reason I'm going to show you right now. So here I have, if you want, a very similar setup to the one that I just showed you. I got a vector v that contains 10, 20, 30. And then I'm going to take a reference inside that vector. So I'm building the variable r as a reference inside that vector. So r is now pointing, if you want, at the first position inside that vector. Then I'm going to copy v into v2. What have we just said? That copy is not a deep copy. That copy is a shallow copy. All that copy does is incrementing a reference counter. And then I'm going to modify r. So I'm going to follow that reference and set it to 99, for instance. So r is a reference inside v. Would you expect v2 to be modified when you modify r? Generally speaking, the answer is no, but in Qt, it is actually, right? If you take a look at the diagram on the right, you can immediately spot why this is happening. It's happening because all the copy did was incrementing a reference counter, and r was still alive, and now r is modifying the data which is shared between v and v2. So modifying r actually has a side effect into v2. Yep, that's a thing. So in principle, when v handed out a reference r, it should have marked itself as not shareable, so that the subsequent copy into v2 should have been a full deep copy, and this problem would have not appeared. But Qt does not do this, because doing this would be terribly expensive, and so you may have this side effect. In a nutshell, if you want a rule of thumb here, is that you should not take copies of Qt containers while holding references inside the data. And by references, I mean things such as actual C++ language references, but also iterators and any kind of pointers inside your own container. Another aspect of all this implicit sharing story is that as soon as you call a non-const function on a container, the first thing that Qt is going to do is to check whether that container is shared, and if it's shared, then it's going to detach it. So let's take a look at this code right here. This code looks pretty innocent if you want. I got a function called calculate something, which I guess calculates something, and then you're going to call it, okay? But let's say I'm not interested into all the data which is returned in that vector. I just want the first result. So what I'm going to do is call that calculate something. That calculate something returns a vector, and then I'm going to take the first element by calling first on that vector. Now you may think that this code is fine, but what if that calculate something returned a vector and that vector is shared for whatever reason? So its reference counter is bigger than 1. Well, that call to first there is actually going to call a non-const method. First, if you take a look at the Qt documentation, has two overloads, the overload for const things, the overload for non-const things. And this is the overload for non-const vector. So that overload, since it's non-const, because it's being called a non-const vector, the one returned by calculate something, does the usual dance. It will check the reference counter, and if it's bigger than 1, it will detach and deep copy. So if by any chance your container was shared, what this code is going to do in one line is going to deep copy the vector, so allocate a new vector, get the first element, and destroy this temporarily allocated vector. Only one go, only one line. That sounds terrible. Well, it sounds terrible to me. And in fact, there is an easy solution, which is calling simply const first instead of first. But how in the world are you going to spot this? This is very hard to do. And in fact, that's when you want to use a little bit of help. You want a little tool to tell you, hey, watch out what you're doing here because this sounds suspicious. Luckily for you, such a tool exists. And the name of the tool, it's called Cladesy or CLazy. It's a tool that the awesome colleague of mine at KDAB started developing a few years back. What it is, it's that it's a simple Clang plugin. So it's something that plugs in into a compiler frontend. And this tool is able to parse your source code as if it was seen by a compiler. And it will detect a number of Qt specific issues. And one of the issues that it's able to detect are calls like this first right here. Calls to non-const functions over Qt containers, where these calls may hide an accidental detach. And if that happens, this tool is going to suggest you to don't use first, because first is potentially detaching. Use another function called const first. That function does exist, just as I said it, const first, and that function is always const, so it will never detach. Now, the nice thing about Cladesy is that then the great developers at the Qt company, especially the one working on Qt Creator, have integrated Cladesy into Creator itself. So these days, as soon as you type that, you're going to get a warning from your editor telling you, wait a second, there is something fishy here. Are you really sure you want to detach this container? And it's very nice to have these warnings in a completely automatic way, in a way that doesn't require you to remember all this stuff. You got this tool, it runs automatically as you type, and it will correct you about these little mistakes about implicit sharing. And while still talking about accidental detaches, you may think that, okay, even if one slips through, it's not the end of the world, it's a little memory allocation, it's a little spike, I can live with that, and my application still works properly, still semantically correct. The full answer to this is actually no. An accidental detach may actually introduce bugs inside your application. To understand why, stay with me for a little bit, because this one is a bit more tricky to see. So what do I have in this little snippet of code is a map, okay, mapping integers to integers. And amongst the many things you can do on a map is to ask it, do you contain a given key? And there are many ways to ask that, but a very simple one is to call the find function on that map, passing the key. And now that find function is going to return an iterator. And that iterator either points to the element with that key, so if it's found, of course, or if it's not found, it's going to return a special iterator pointing to the so-called end of the map. So how can you build such a check? Well, you can simply ask, does the map contain the key by calling find? And then you compare the iterator returned from find with the iterator pointing to the end of the map, so cend. And so you ask, you do this comparison. If the two are equal, then you know that the key is not in the map and you print not found. Otherwise, you know the key is in the map and you print found. So this looks legit. Where's the problem with this code? The problem is, as usual, that find is a non-const function. When you call find on a map, what kind of iterator you get? And especially when you call find on a non-const map. That's right, you get a mutating iterator. So you get an iterator that you can use to modify the contents of the map. And since that's a possibility, what find does is to detach the map. Well, it may detach the map. That depends on whether the map is shared or not. But let's say it is. Let's say that the map is actually shared when you call find on it. So the first thing find does is to detach the map, and then it will search for the key inside its detached copy and return an iterator to the key value pair if it's in there, or to the end if it's not there. All this makes sense, and all this is correct. But what else are we doing in the same statement? I'm calling map cend, so I'm taking an iterator pointing to the end of the map. And the kick here is this. Which one is done first? Do you first call find and therefore detach the map if it's necessary and then search? Or do you first call cend and so get the iterator pointing to the end? And the order in which you do these two operations is essential to understand why this code might be wrong. And what do I mean by this? Well, if you call find first, then everything is fine, because then cend is going to act on the detached map, and there is no problem there. But again, stay with me with 1 minute. What does happen if you call cend first and then find later? And before you're wondering, wait a second, why should the compiler do this? Well, let me tell you, C++ does not give you any specific ordering to these two operations on the two sides of an equal operator. Either side can go first. So this is a concrete possibility. Your compiler may call cend first and find second. So what happens if you call cend first? Cend is just going to return an iterator pointing to the end of the map. That's fine. Then you call find, and find detaches the map. Okay? And let's say it does not find the key. So it returns an iterator pointing to the end. But to the end of which map? Is it the same as cend? It's not the same anymore. It's the detached map. So in other words, find key may return an iterator pointing to a different end than the one that you had before, the one that cend returned. Cend returns the end of the shared map, and find returns the end of the map after the detach has happened. Yep. And so the two iterators may actually compare different, and therefore we're going to print found even if the key is not in the map, because find returned an iterator pointing to the end. It just wasn't the end you were expecting. So how do we cope with this? Clearly, this is a problem, and the solution is always the same. There is a const find overload that will allow you to avoid this issue, because const find will return a const iterator, not a mutating iterator. The better solution is you should avoid mixing iterators and const iterators when working on Qt containers, because they simply don't mix and because they hide bugs such as this one. But even better solution is use Cladesy. Cladesy will find these sort of things and point them out to you, telling you, wait a second, this code is fishy. Did you really mean to call find and mix it with cend? Are you sure you didn't mean const find and cend? Or maybe find and end without the C, so the non-const end function. Which one is it? And by having a warning, at least you now know that there is something wrong there, something that deserves your attention, and indeed the fix is super simple to deploy, just deploy it and move on. Whoa, by now you should be thinking, wait a minute, this implicit sharing thing is terrible, why did Qt go with it? Again, it's the but sometimes syndrome. Implicit sharing works in a huge majority of cases. It just has a few corner cases in which it doesn't work, but we have workarounds, we have trade-offs that cover all these corner cases. So don't worry too much about it. In fact, if you're wondering, did Qt at any time decide to move away from it? Sure that the temptation is there, but also no, Qt is not moving away from it. So even in Qt 6, Qt still has implicit sharing in all these classes, all the containers, most of the value classes. They all feature this. There have been, however, some minor changes to the explanations that I just gave to you. Specifically, things such as QList, QVector, QString, these kind of classes are no longer just one pointer inside, but as a little trade-off there, their size has grown a little bit. Now there are 3 pointers inside, because there is not just the pointer to the pinball, there is also a shortcut pointer pointing to the beginning of the actual payload. It's just a little trade-off. That doesn't mean that the implicit sharing is gone. Implicit sharing for all these classes is still there, and it's there to stay. Okay, this concludes today's video, but we're not quite done with implicit sharing just yet. There is one more video, the next one, in which I'm going to discuss how implicit sharing mixes or does not mix with the C++11 range-based for loop. So stay tuned for that one, and as usual, have a good day.